Welcome to the deep dive. We're jumping straight in today with planetary boundaries. It's this really core idea for understanding Earth's health. Think of it like the planet's operating manual, defining that safe zone for us within Earth's own limits. But if you push too hard, well, you risk tipping these systems into states we really don't want. And the science is pretty clear. We've already done that for several key boundaries.
That's absolutely right. The framework looks at 9 really critical Earth system processes. Some, like the ozone layer, we've actually managed to step back a bit, which is good news. But others are, well, they're flashing some pretty clear warning signs.
And today, our focus is squarely on one of those vital ones, ocean acidification. OA, you often hear it called. You've probably heard the term, but let's just quickly nail down what it means. Basically, the ocean soaks up a huge amount of the extra CO2 we pump into the atmosphere, mainly from burning fossil fuels, right?
Exactly. It acts as this massive carbon sink, which, on one hand, helps slow down climate change a bit. But the flip side is it changes the actual chemistry of the seawater. It lowers the pH, makes it more acidic, and crucially, it reduces the amount of available carbonate ions.
And that chemical change, that's the problem for marine life, especially the ones building shells.
Precisely. Think corals, oysters, clams, even these tiny but vital plankton called pteropods. They build shells and skeletons from calcium carbonate. And their ability to do that hinges on something called the aragonite saturation state, ARAG for short. As that state, that ARAG drops, it gets harder for them to build and maintain those structures. And if it drops too low, well, their shells can actually start to dissolve.
Okay. Now, I remember in earlier looks at these planetary boundaries, ocean acidification was seen as sort of right on the edge, like at the margin, but maybe not fully crossed yet, globally speaking.
Yeah, that was the assessment. It felt like we were approaching a danger zone, but maybe not quite in it on a global average level.
That assessment, it was based on the best understanding at the time.
Oh, absolutely. It reflected the data and the models we had then.
Yeah.
But, science moves on. We get better data, refine the models.
And that's exactly where we're heading today. We've got this really significant new research paper. It takes a much, much deeper look at that OA boundary. And it's not just an update, is it? It uses the latest data, the best models. It tackles uncertainties head on.
And it looks at different ocean regions, different depths. And I think most importantly, it connects the chemistry directly to how key marine species are actually doing.
Right. So our mission today is to unpack what this, let's call it refined analysis, really tells us. What's the current state, and what does it mean for the safe operating space for the oceans?
Yeah, and spoiler alert, It paints a rather different picture than we had before.
Okay, let's rewind a bit first. That original thinking, how exactly was the OA boundary first defined?
Sure. So the initial boundary proposed back in 2009, I believe, was set based on this idea of limiting the reduction in the average global surface aragonite saturation state, ARAG again. The limit was set at no more than a 20% reduction compared to pre-industrial levels. So before we started burning fossil fuels on a massive scale, that 20% drop was the line.
20% globally. Why that specific number? What was the goal behind setting that threshold?
Well, there are really 2 main concerns driving it. One was trying to stop the surface waters in polar regions from becoming undersaturated. That means ARAG dropping below 1, because that's the chemical point where calcium carbonate structures literally start to dissolve. So keeping polar waters above 1 was key.
Okay, protect the poles. What was the other concern?
The other was warm water coral reefs. They need much higher levels for healthy growth. Generally, ARAG needs to be above 3.5 for good calcification. So that 20% global average reduction target was kind of aimed at trying to keep conditions broadly okay for both those really sensitive systems, polar waters and tropical reefs.
But you mentioned it had limitations, this original definition. It was acknowledged even then.
Yes, definitely. It was understood to be, let's say, a relatively simple approach for a complex problem. It used a single number for the pre-industrial ARAG, didn't really formally bake in the uncertainties around that number or in the modern measurements and models. And critically, perhaps, it focused mostly on the global average at the surface. It didn't get into the weeds of regional differences or what was happening deeper down.
Right, which leads us neatly into this new research. How does this assessment get past those limitations? What makes it give us a clearer picture?
Well, it basically leverages all the progress we've made in the last decade or so, much better ocean data, more sophisticated Earth system models.
Yeah.
And the key improvements really target those earlier simplifications directly.
Okay, let's break those down. Incorporating uncertainty, that sounds fundamental.
Oh, it's absolutely vital. The original boundary was essentially one line drawn in the sand based on averages. This new work brings in the range of uncertainty. Uncertainty in guessing the pre-industrial conditions, and uncertainty in our current measurements and models. It treats these values not as fixed points, but as, ranges of probability.
So instead of a sharp line, it's more like a fuzzy zone, a risk zone.
Exactly. Instead of just saying 20%, it's more like 20% plus or minus this much. That fundamentally changes how you assess if you've crossed a boundary.
Okay, got it. And they didn't just look at the global average anymore.
No, they really zoomed in. They broke the ocean down into distinct regions. Because let's face it, ocean acidification isn't happening uniformly everywhere, is it? Conditions can change much faster, or areas might be naturally more sensitive, like polar regions or certain coasts. A global average can easily hide really critical local or regional problems.
And they went deeper too, you said, below the surface.
Critically, yes. They didn't just look at the very top layer. They analyzed changes down at 50 meters, 100 meters, even 200 meters. The ocean isn't just a skin. There are huge ecosystems, important fisheries, carbon storage happening at these depths, and they're also being hit by CO2 uptake and other stuff.
And the last piece of the biology, tying the chemistry directly to life, that feels like a big shift.
I think it's arguably the most impactful improvement. The original boundary used chemistry mostly as a proxy for biological safety. This new research uses specific biological indicators. These are species or habitats we know are sensitive to OA, like pteropods, corals, shellfish. They use actual biological data and expert knowledge to ask what chemical conditions represent marginal or unsafe from an ecological point of view. Then they check how current chemistry stacks up against those biological thresholds.
Okay, that makes a lot of sense. So using these more sophisticated tools, this deeper analysis, what does it tell us about where things stood, say, around 2020?
All right, let's look at the updated numbers. Global average, surface ocean first. Using the latest data and models, they found the average surface ARAG in 2020 was about 2.90. Compare that to the estimated pre-industrial average of 3.51. So doing the math, that's a reduction of around 16%.
16%. Okay, the original boundary was 20%, so 16% on its own. That still sounds like we're close, maybe still just at the margin. Seems kind of consistent with the old view.
But this is where that uncertainty piece really kicks in and changes the story. Remember, the boundary isn't just a line, it's that fuzzy zone. When you factor in the uncertainty in the boundary definition itself, the wiggle room around the pre-industrial value and the 20% target, that boundary zone works out to be 20% plus or minus about 5.3%.
Okay, I'm following.
Now, take the current state, that 16% reduction we just talked about, and apply the uncertainty around that measurement too. When you do that, the current state is actually best described as a 17.3% reduction, plus or minus 5.0%. And here's the key. The current range, 17.3 and I's 5.0%, actually overlaps with, it falls within, the uncertain boundary range, 29 is 5.3%.
Wait a second. So, hang on. We're not just near the edge of the old safe zone. By properly accounting for how well we actually know the numbers, we're already operating inside that zone of uncertainty and higher risk globally for the surface.
That's exactly it.
Yeah.
It shifts the whole perspective. It's not at the margin anymore. It's already inside the uncertain boundary zone, just based on the inherent fuzziness of the data.
Okay, wow. And they looked beyond the average too, you said, at the area affected.
Yes, absolutely. Looking at the actual proportion of the ocean surface that has crossed that original 20% threshold, setting aside the global average for a moment, using a, let's say, precautionary approach within the pre-industrial range, the analysis shows that over 40% of the global surface ocean area had already seen a 20% or bigger drop in ARAG by 2020.
Over 40% of the area, that feels way more significant than just an average number nudging closer.
It's a huge chunk of the ocean surface, yeah.
And what about different regions? Did that picture vary?
It did. They looked at 7 major ocean basins. And get this, 4 of them, the Arctic, the North Pacific, the Southern Ocean, and the North Atlantic, have already, on average for that specific basin, crossed the original 20% reduction boundary. And maybe even more telling, all 7 major ocean basins have already crossed the lower limit of that uncertain boundary range. So even the parts we thought were maybe more resistant, they are clearly in the risk zone now too.
So the chemistry alone, once you account for uncertainty, area, regions, it already shows we're in deeper trouble than we thought. But let's bring in the biology. How are those key habitats and species actually doing under these conditions?
Right. This is where those biological indicators really hit home. Because, the chemical numbers define the boundary, but what ultimately matters is how life is coping, isn't it?
Let's start with those original concerns. Polar oceans and tropical corals. How are they looking now?
Okay, polar oceans. The original idea was keep the average surface ARAG above 1 to prevent dissolution. Well, the annual average is mostly still above 1, that's true. But the area of polar surface water that dips below 1, becoming undersaturated seasonally, is growing fast, really fast. The paper found about 21% of Arctic surface waters were undersaturated in the 2020s. Compare that to maybe 5% pre-industrially. That's a four-fold increase in the area where shells are actively at risk of dissolving.
Fourfold increase in area. Okay, so the average doesn't capture that seasonal risk.
Exactly. Area and those seasonal lows matter much more than just the annual average for the creatures living there.
And speaking of creatures, what about things like pteropods? Those little sea snails, crucial food source up there.
Yeah, pteropods are super vulnerable. Their shells are aragonite. The paper looked at thresholds linked to real biological impacts. ARAG below 1.5 causing mild shell dissolution, and below 1.2 causing severe dissolution. The analysis. It shows huge areas of their habitat down to 200 meters where they live are already experiencing conditions below these danger levels. The area where conditions cause mild dissolution. It increased by something like 61% between pre-industrial times and 2020. 61% increase.
Right.
And now, about 80% of their polar habitat, down to 200 meters, is at or below the conditions needed for mild shell dissolution. It's a massive potential hit to a cornerstone of the food web.
80%. That's
Yeah.
genuinely alarming. Okay, what about the other end of the spectrum? Tropical corals. They support so much biodiversity.
Yeah, corals are critical. Biodiversity hotspots, fisheries nurseries, coastal protection. Just hugely important. For them, the threshold for marginal conditions where growth and calcification start getting really stressed is generally seen as ARAG dropping below 3.5. And the paper's analysis shows that the average surface ARAG in the big tropical reef zones, think Central Pacific, Central Atlantic, Indian Ocean, is already below that 3.5 level today.
So even if the total reduction in those areas hasn't hit that global 20% target yet, the actual level is already marginal for healthy coral growth.
That's it exactly. The absolute number matters to the organism. So marginal conditions for coral reefs are already widespread across the globe. If you look at the area experiencing these marginal conditions in the tropics, it went up by 43% between 1750 and 2020. The amount of truly suitable habitat for coral growth is shrinking significantly.
And the study also looked at coastal bivalves like oysters and mussels. Why were they included?
Well, they're ecologically vital filter feeders, habitat structure, and of course hugely important for coastal aquaculture, economies, food security. The paper identified a threshold for marginal conditions for their growth or production at ARAG below 1.8. Globally, the area of coastal habitat crossing that line has increased by about 12% since pre-industrial times. And today, roughly 18.6% of global coastal habitat is considered marginal for bivalve production, just based on this OA chemistry.
And coastal zones are complicated places, aren't they? You've got river runoff, sometimes pollution.
Precisely. They're super dynamic, lots of interacting stressors. So while these global models give us the big picture on OA, the actual local impacts on shellfish farms or natural beds could be, well, even worse in many spots because OA is piling on top of other issues.
Okay, we've talked a lot about the surface, coasts, but you mentioned this paper went deeper. What do they find happening in the subsurface ocean?
Yeah, this is another really crucial part of the picture. They look down to 200 meters, that's the upper twilight zone, habitat for loads of fish and other life. And significant OA changes are definitely happening down there too. It's driven by CO2 uptake from the surface, sure, but also by things like organic matter sinking and breaking down, which releases more CO2 at depth.
And how does the area affected down there compare to the surface? Is it similar?
Actually, in terms of the area that's crossed that original 20% reduction boundary, it's more extensive in the subsurface than at the surface. Remember, it was about 40% for the surface by 2020. Well, at 50 meters depth, it's around 44%. At 100 meters, it's up to 58.3%. And at 200 meters depth, it's a staggering 61% of the ocean area.
61% at 200 meters has already crossed that old 20% line. Wow. So the problem is definitely not just skin deep.
Not at all.
Yeah.
And these changes at depth, they have huge implications, right? You're talking about deep water corals, crucial habitat for many commercial fish species that move up and down, plus the ocean's role in storing carbon long term. A key concept they talk about is the shoaling of the aragonite saturation horizon. Think of that horizon as the depth where water chemistry flips, and below it, calcium carbonate tends to dissolve. As the ocean acidifies from the top down, that boundary gets shallower and shallower. It's rising up.
Ah, so it creates like a squeeze.
Exactly, a vertical squeeze on habitat. Organisms that need to build shells and live below a certain depth find their safe space shrinking from below at the same time as conditions might be changing at the surface too.
Okay, so putting this all together, The original 20% boundary, maybe a decent first try, but it looks like it wasn't really protective enough once you factor in uncertainty, regions, the deep ocean, and especially the actual biological impacts we're already seeing. Given all this new evidence, what boundary does this paper suggest we should be aiming for? What's a more appropriate target for a truly safe operating space?
Well, based on everything, the uncertainty, the widespread impacts already happening regionally and deep down, the fact that key biological systems are clearly stressed. Now, the paper argues pretty strongly that we need a much more conservative boundary, a stricter one.
Okay, more conservative. What is it? What's the proposed revised boundary?
They propose setting the ocean acidification boundary at a 10% reduction from the pre-industrial average global surface area.
10%. Okay, that's cutting the allowable reduction in half compared to the original. Why 10%? What makes that a better target?
It's seen as more protective because the analysis showed that staying within a 10% reduction does a much better job of actually limiting those unacceptable changes we're already seeing. For instance, at 10% reduction, you'd keep the area of Arctic surface water going undersaturated below 10% instead of the 21% we have now. It also significantly cuts down the area where polar pteropods face shell dissolution.
And what about for corals and shellfish? Does 10% help them more too?
Yes, considerably. A 10% limit is much better at keeping conditions in the tropics suitable for healthy coral growth. It limits the loss of that good habitat to around 28%, compared to the 43% increase in marginal area we've already hit. And for coastal bivalves, it keeps the amount of marginal habitat globally closer to 10%, rather than the nearly 19% it is now. It's basically a level designed to offer more genuine protection to these really vulnerable systems based on the biological evidence.
That definitely spells out why 10% makes more ecological sense. But here's the kicker. If that's the real line in the sand for the safe zone, when did we actually cross that boundary?
Yeah, this is perhaps the most sobering finding related to the 10% boundary, according to their analysis using the models and data available. This more stringent, more ecologically relevant boundary, a 10% reduction. We first crossed it globally sometime during the 1980s.
The 80s. You're saying we passed this more appropriate safe limit decades ago?
That's what the analysis indicates, yes. And it shows that the entire global surface ocean had passed this more conservative 10% reduction boundary by the early 2000s.
Wow. So the warning light wasn't just starting to blink recently. Based on this more refined understanding, it effectively turned solid red a long, long time ago.
Pretty much. It fundamentally reframes when the transgression occurred.
Okay, so let's pull this all together then. What's the big takeaway here? What does this new analysis really mean for how we understand OA and where we stand?
I think the fundamental takeaway is that the previous assessment of the OA boundary, while well-intentioned, likely underestimated the true risk. Based on this updated science bringing in uncertainty, regions, depth, and crucially, those biological impacts were not just nearing a risk zone. We're already deep inside it. We crossed a more scientifically sound and ecologically meaningful safe boundary decades ago.
And the cause is still crystal clear, presumably.
Oh, absolutely undeniable. The driver is our anthropogenic CO2 emissions. Full stop. The paper even looks ahead. It projects that only a really ambitious low-emissions future, like the pathway known as SSP 12.6, which needs massive global cuts, might potentially keep some ocean areas within even the original 20% boundary by 2100, with maybe some recovery later on. Higher emissions, they lead to almost the entire surface ocean blowing past a 40% reduction by century's end. The impacts would be catastrophic. So halting this means urgent, drastic CO2 cuts and exploring atmospheric greenhouse gas removal.
And it's important to remember OA isn't happening in a vacuum, right? The ocean's facing other pressures too.
That's such a critical point. Ocean acidification interacts with ocean warming, with decreasing oxygen levels, deoxygenation. These stressors often gang up on marine life. Their combined impact can be much worse than any single stressor acting alone. We really need more research to understand these complex interactions better, and we need better data, especially for coastal areas and extreme events.
So this improved understanding, this refined boundary, it's not just academic number crunching. It has real-world implications for how we manage and protect the oceans, doesn't it?
Absolutely. Having a more accurate picture of where the real danger line is and knowing we're already past it provides a much stronger scientific basis for conservation strategies. For policy decisions, think global biodiversity agreements. It really underscores the urgency. It helps pinpoint the most vulnerable regions, the species most at risk that need targeted protection, and revealing these major impacts deeper down. That tells us we need to broaden our conservation thinking way beyond just surface waters and coasts.
This deep dive really has shifted the perspective. It shows that the warning signal on ocean acidification, well, it's not just blinking anymore. It's been solid red for decades, especially when you look beyond the simple global average and really consider the biology, the different regions, and the deep ocean.
Yeah, it makes it starkly clear that crossing this boundary isn't just about chemistry changing on a chart. It's about fundamentally altering the environment that life in the ocean depends on. It hits entire habitats, the ecosystems, the services they provide us, everything from tiny plankton at the base of polar food webs to iconic coral reefs to the coastal fisheries that feed millions. It's all interconnected.
Thinking about those changes, that image you mentioned from the paper really sticks with me, that shoaling of the aragonite saturation horizon, this chemical boundary rising up hundreds of meters in some places. What does it truly mean for marine life when we create this vertical squeeze from below at the same time as warming forces species to shift horizontally, maybe poleward or deeper? How does this multidimensional pressure cooker challenge our whole way of thinking about marine conservation, about resilience, about the future of life in the ocean? It's a profound question this science leaves us with.